In the last class, I was showing you a lot of calculations about how to use wave functions as probability densities. And maybe it was a little bit dry or a little bit abstract. So just as a change of pace, let me show you a couple of examples of movies of possible wave functions using this software Mathematica. This is a demonstration that's up here on my screen. So by the way, have any of you used this Mathematica? Do any of you know what I'm working with? No. Okay, well,
I'm learning.
I see one nod, mostly knows.
Very briefly.
Okay, so, okay, maybe another one. Okay, great. Yeah, so I love this software. As I mentioned, I use this every day. And I'm going to post the examples that I work with on the Google Drive site for the class. And I really do recommend that you should download the software following the instructions in the syllabus. And then download my examples and try them out. And then you can make little changes and see what happens. All right, and I'll be glad to answer any questions if you get stuck with software things. So here to begin with is an example that is sort of similar to the stuff that I was showing you yesterday. Right, so here's an example of an unnormalized wave function that somebody might give you to start with. You can see things I highlight with my mouse, right? Okay, so this is an example of an unnormalized wave function. That's some unknown coefficient A. A is for amplitude, okay? So capital A times an exponential of minus alpha times x squared. So that's the position dependence. And then an exponential of minus I omega t. That's the time dependence. I typed this into Mathematica, and then my quick little tip is that to get Mathematica to execute the command, you push Shift Enter. Right? That this is how we laugh at newbies, right? We say, newbies, you just keep pushing enter and nothing happens, right? But it's shift enter. That's what makes something happen, right? So you push shift enter, and then Mathematica echoes back to you its version of what you just typed. And so this is A times the exponential, and then it's rearranged the terms. So it's minus x squared times alpha, and then minus IT omega. So that's just like what I typed in, just rearranging the factors. The I, by the way, that Mathematica recognizes as the square root of -1, that's a special I. That's not just the I that you get by typing I on the keyboard. Okay, so this is our unnormalized wave function, right? If we want the complex conjugate, well, I could try just typing conjugate of that thing, but Mathematica does not process it in the way that I wanted it to, right? Mathematica just says, oh, I'll take the complex conjugate of everything. Okay, that's because Mathematica is being super conservative. And so it does not assume that any of the numbers that I typed are real. It thinks, oh, any of these things, they might be complex numbers, X or T or anything like that. Right? So if I really want Mathematica to simplify that in the way that you and I know that we want it to be simplified, I have to make a whole bunch of assumptions, okay? And so I say, let's assume that X is real, and T is real, and A is real, and omega is real, And alpha, well, not only is it real, it's also has to be positive. Positive is a subset of real. And so I tell Mathematica to make all these assumptions, and then Mathematica can simplify it to be the way that I want, which is that it's just like what I started with, except that the minus I is changed into a plus I times omega t. By the way, in the class yesterday, I pointed out that the A can actually be complex, but for the moment, I'll just assume that A is real, and that makes things easier. But in general, the amplitude A in front of everything can be complex. Okay, you good with this so far? You know what you're looking at? All right. So now, as I told you yesterday, first step has got to be to make sure the wave function is normalized. Okay? So I tell Mathematica, calculate this normalization integral. That is, integrate the product of psi star times psi for x goes from minus infinity to infinity. And when you're doing that integral, assume that A is positive. Okay? So here's the result of doing that integral. I'm sure glad I have a computer to do that integral for me. That could be a hard integral otherwise, but luckily the computer can do it in a fraction of a second. Okay, so now I want to make sure that this thing is 1. So I say, solve the equation that normalization integral equals 1, and solve that for this number A. You might notice, by the way, that when I have an equation to be solved, it has a double equal sign there instead of just a single equal sign. A single equal sign is a command that says, set this equal to that, right? But a double equal sign means a statement that might be true or false, right? Is this thing equal to that? And so that can be an equation to be solved. Right? So Mathematica solves it. It gives 2 possible solutions for A. Right? A can be a negative number or a positive number. That's because I told it that A is real. Actually, if I had left A as a complex number, then it could only solve for the magnitude of the complex number. It couldn't solve for the phase. Okay, so now I say psi should be the unnormalized psi, and then I will substitute in the normalization. Okay, so this slash dot means substitute in something. So I want to substitute in the normalization. And so which of the normalization things should I choose, the positive one or the negative one? Well, it doesn't really matter, but I'll choose the positive one. Okay, so that's the second of the normalization things. That's this 2 on the list. All right, so here is the psi with the normalization substituted in. Okay. And then for psi star, I'll take the unnormalized psi star and substitute in the second normalization thing. Okay. So that makes this psi star. Okay. So here, I haven't been executing all these commands as I go along, but I can. They only take a second. All right, so there's psi and psi star with the normalization. Right? So now, well, just to double check, let's calculate the normalization integral again, just to make sure it's 1. Phew, okay, it's 1. Yes, good. Okay, so with this psi and this psi star, the normalization integral comes out to be 1. Okay, so this is a nice example of a normalized wave function, which depends on position and time. So what can I do with it, right? Well, for one thing, I can make a plot. Let's visualize it, okay? So to visualize it, well, it's a complex number, so it has a real part and an imaginary part. If I want to make a plot of it, I better plot the real part and the imaginary part, okay? So that's the blue curve is the real part, and the orange curve is the imaginary part. Okay? So I'm plotting both of these things as functions of x at different times. Okay, so I'm making an animation that shows how these things depend on time. How the plot is the real part as a function of x and the imaginary part as a function of x, and then the plot keeps getting updated for different times. Okay, so is that clear enough what we're looking at? Maybe, okay. Ooh, if I really wanted to be clever, I would label my axes. That would be a nice thing to do, wouldn't it? Okay, so I'll say axes label, go to, how about x and, oops. Escape. This is a trick for writing Greek letters. Okay, there's a plot with axes that are labeled. That's even better, isn't it? Okay, so it shows the real part and the imaginary part as functions of x for different times. Okay, so you can see these things are waving back and forth in time, but nothing's really going anywhere in x. That's how a wave function might look. Then what? Okay, then we could calculate the probability density. Okay, the probability density is the magnitude of psi squared. Okay, so here it is. And you can see it doesn't depend on time, right? That the time factors canceled. Okay? So now I'll make a movie of the probability density. Okay, here it is, right? It's a very boring movie because it doesn't depend on time, right? It's constant, right? So that's what it looks like. Maybe I should label the axes on this one also. Okay, so I'll say axes label, go to x and p. All right, there's my boring movie of x and p. Okay, so the particle is probably around here. Okay, so the probability density is concentrated near the origin. And in this particular example, it's not going anywhere, right? The particle is staying close to the origin. I should say, by the way, in this movie, the boring movie, I have to put in numbers, right? And in order to have a numerical thing to plot. So I'm just making a sample movie with specific values of all the things, omega and alpha. Okay. We could also say, what happens if I change the alpha? Like what happens if that alpha parameter, the thing in front of X, is 10 instead of 1? Ooh, then it's a distribution that's extremely concentrated near the origin. In fact, maybe I should even change the plot range. There, it's something that's extremely concentrated near the origin. Okay. If I go to alpha is 1, it's more spread out. Okay. If I go to alpha is 0.1, it's even more spread out. Then here, I'll go back to 1. I could calculate what's the probability that the particle is between certain positions. Okay. So for example, I could say, what's the probability that the particle is between 1 and 2? Okay. So I'll tell Mathematica then to integrate the probability density between the two positions that I care about. Okay, so between 1 and 2. Mathematica can actually calculate an exact answer for that in terms of this function called ERF. ERF stands for error function, which is a function that you might or might not have ever heard of before, but you know, it's a function. Mathematica knows it. Okay. But if I want to know it numerically, I can just substitute in a particular number for alpha. So if I have alpha is equal to 0.1, then it says the probability that the particle is between 1 and 2 is about 2%. So that's saying then that this area, the area under the curve here between 1 and 2, this is 2% of the total area under the curve everywhere. If I change alpha, if I make alpha to be 10, for example, then it looks like the area under this curve between 1 and 2 is really small. I can't even see it, right? It's hardly anything. And Mathematica says that is an area of 10 to the minus 10. Okay, so if the particle is really concentrated here, it looks like it's really concentrated for X between minus a half and a half. Okay, so the probability that the particle is out here between 1 and 2, well, it's not quite 0, but it's like 10 to the minus 10. It's extremely small. Okay, if alpha is a number like 0.1, whoops, 0.1, right? With this value of alpha, there's actually quite a big probability that the particle is between 1 and 2. Okay, and Mathematica calculates that is a 16% probability that the particle is between 1 and 2. Okay, here, the axes are not the greatest. Let's see, can I say 0 to there? That's a nice one. Yeah, you can see there's a big chance that the particle is out here. Okay. Here, I'll put this back to 1. Okay, now we can calculate averages, that is expectation values. Okay, so here's the average of X, right? I'll tell Mathematica to make the integral sandwich, like we talked about yesterday. All right, so I tell Mathematica calculate the integral of psi star times X times psi, integrating for X from minus infinity to infinity. And that integral is equal to 0, which is not a surprise because the curve is totally symmetrical between negative X and positive X, right? There's the same chance to have X be positive or negative. So the average will be 0. Okay. How about the average of X squared? All right, so I'll tell Mathematica, I'll do another integral sandwich, right? So psi star times X squared times psi. And that comes out to be 1/4 alpha. Right? So the variance of X is the average of X squared minus the average of X, quantity squared, just like what we were talking about. So that is 1/4 alpha. Okay? The standard deviation, that is to say, the uncertainty in X, how broad is the distribution? That's the square root of the variance. So 1/2 root alpha. Right? So it says that when alpha is big, there's a really small variance, right? That's what we already saw, right? When I made alpha to be 10, variance was really small. When I made alpha to be small, the variance was really big. The standard deviation was big. The uncertainty in X was big. All right, so that's my my first demo. Okay, questions about this, right? So you have questions about the software or about the science, either way. Right? Okay. So, you know, when you download this, you know, you can change numbers and see what happens, right? And so even if you don't know the whole syntax for Mathematica, you can just change specific things. Like if there can be a line where it says alpha goes to 0.1, and you say, I wonder what would happen if alpha is 0.01. So you just type 0.01 instead of 0.1, right? And then you click Shift Enter, not Enter, Shift Enter, and then you see what it does. Hopefully that'll work for you. And if it doesn't, you can ask me questions. All right, let me show you a variation on this demo. Okay, so I'll show you the same kind of thing, but with a different wave function. So let's see, I go to share and I'll do my other demo. Okay, you see my other demo now? All right, so this is very similar to my first demo, but I'm starting with a different unnormalized wave function. Right? So this one has 2 terms. It has the first term that's just the same as what we had before. And then we have a second term, which is very similar, but it has just an extra factor of X in the front. A times X times this exponential. And then it has a different time dependence, e to the minus 2i omega t. Okay, so I can run that one and calculate the complex conjugate. Okay, so now I'll just repeat all the same steps that I did before. Okay, so I can normalize this thing. So I calculate the normalization integral and set it equal to 1. Now I'm really glad I have a computer to do the integration for me. Okay, so I get, a can be plus or minus this thing. I'll choose the positive one. Okay, so with that assumption, I get this function for psi and this function for psi star. And the normalization integral is 1. Okay. Now, what I really want to show you is, what does the movie look like if we had this wave function? Okay, so let's look at it. Here is a movie, and you can see that this movie looks maybe a little bit more interesting than our last movie, right? That in this movie, there are still, the real and imaginary part are going up and down, but now it looks like they're kind of sloshing back and forth, right? It's not just going up and down in place, but there's some side to side also. Okay. So now let's find the probability density that goes with this movie. Okay. So I have psi star times psi, and we can see there's time factors in there. Okay, so there's this whole messy expression. I haven't simplified it. Okay, but in term number 2 there, and term number 3, there's some times. Okay, so there's some time dependence now. So I can make a plot of the probability density, and it now is not quite as boring as the last plot, right? Because now the probability density is sort of sloshing back and forth. Okay, so we can now calculate averages of things, and the averages will have to depend on time, right? Or I could calculate, like, what's the probability that X is between 1 and 2, and that probability will depend on time. Okay. So here, let's calculate the average of X. I'll integrate the sandwich, psi star psi, psi star times X times psi, for X from minus infinity to infinity. And look, it has a time dependence, right? It's something times the cosine of omega t. So it looks like what you remember from a harmonic oscillator, right? In classical mechanics, right? A harmonic oscillator has X that is like the cosine of omega t. All right, so all right, the average X now has this time dependence. How about the average X squared? Well, that's this integral. Actually, it turns out it doesn't have any time dependence. It has this complicated dependence on alpha, but not on time. So the uncertainty, well, there's the variance sigma squared, that is the average of X squared minus the average of X, quantity squared. Okay, so that has this time dependence. And then if I go to take the square root of that, here's the standard deviation of X. That's the uncertainty in X. And it has a little bit of time dependence. It gets wider and narrower, right? And that kind of goes along with what you see in this movie up here, right? You can see as the probability goes back and forth, sometimes it's wider and sometimes it's narrower. Okay? So the equations really correspond to something that you can see with your eyes, right? When you look at the plots, right? You can see how the probability is shifting left and right. And you can also see that the probability is getting wider and narrower, right? As the time goes back and forth. Okay, so, you know, your goal should be to see the same physical principles in different ways, right? Both to see them with the equations and then also see them with graphs or movies, right? To see what is the shape of the plots, what does it signify physically, right? And so going back and forth between these things is especially, I'd say, preparation for the physics GRE. If any of you have any of you taken the physics GRE, or any of you planning to take it? Yes? So Mahisha, yes? Or no? Okay. Well, okay. So, I mean, what I remember from the physics GRE 40 years ago, not the most up-to-date information, is that it had a lot of questions about sort of basic quantum mechanics. It didn't include advanced quantum mechanics, but there was a lot of basic quantum mechanics of saying, you know, if you have a wave function that looks like this, what can you infer from that, right? And so this sort of exercise of having practice looking at the wave function or looking at the probability distribution is you know, preparation for that sort of thing. Okay, what else can I say about this? One thing I could say is, you know, certainly we have things that are depending on time, right? The average X is depending on time. So it stands to reason there must be some velocity embedded in here, right? You know that velocity is associated with the change of position. So you might say, well, what can we calculate about velocity? Okay, so let's try doing some velocity calculations now. All right, so I'm going to go back to the iPad for doing some velocity calculations, and then we can come back to the demos again later. All right, any questions about the demos before I turn these things off? No. You guys are so quiet, and I have no idea if that means that this is all just so easy for you, or if it means that this is all just so hard for you. You have absolutely no idea of what I'm talking about. So how can I find out? Which is it, too easy or too hard? Not exactly sure. All right.
I think it's somewhere in the middle.
Somewhere in the middle.
Some of this is familiar, some of it's not.
All right. That's all right then. Which parts are familiar?
I think like the like we calculated before, like the probability and like the integral in a range, I believe.
Mm-hmm.
But like
so you've done that sort of thing for other kinds of probabilities, maybe not for quantum mechanics. Is that how it goes?
I want to say like in the beginning of modern, we touched on it, but nothing real heavy.
Okay. All right. Well, let's suppose you want to know something about velocity. Okay. So you know, we have that an average position. You can see my iPad now, right? Okay, good. The average position is an integral with the normalized wave function of psi star of x and t times x times psi of x and t dx. All right. And you know that this might or might not depend on time, right? Because you've seen examples both ways, right? In the first example, it doesn't depend on time. And in the second example, it does depend on time. So it might depend on time. And then we could say, well, what about the velocity? How does this thing depend or not depend on time? Okay, so we could say the average velocity should be the time derivative of the average position. That makes sense, right? And so we should be able to calculate it by taking the time derivative of this integral. Star of x and t and x times psi of x and t dx. Okay, so let's take the time derivative of this integral. Okay, so this is actually very similar to a problem that I did yesterday, right? Yesterday, I did the time derivative of the integral without this factor of x in the middle, right? And I proved for you that the time derivative of that is 0. So the normalization integral is constant. Okay, so now I'm going to do a similar thing, but including the factor of x inside the sandwich to see how this average of x is changing in time. Okay, so let's do it. Okay, so if I want to take the time derivative of this integral, we can say, well, what depends on time? Okay, well, the limits of integration do not depend on time. Okay? Because they don't depend on time, I can take the time derivative and put it inside the integral. So I get, wrong pen, I get the integral of the time derivative of psi star times x times psi. This thing integrated over x. Okay, so it's the derivative of a product of 3 things. One of those things, x, doesn't depend on time. So I can take it out of the derivative. It is, you know, it doesn't have any explicit time dependence, right? I mean, the average of x depends on time, it might, but x just as a variable by itself is separate from time. Okay, so then what? So I can factor out the x, and I have the time derivative of the product of psi star times psi. Okay, well, have to use the product rule, right? So that makes the psi star times the derivative of psi plus derivative of psi star times psi. In fact, all of that stuff is just what we talked about in the last class. So I'm not going to do it again. I'll just use the thing that I already derived in the last class. Okay, what we derived in the last class is that all this simplifies to IH bar over 2m, and then, whoops, the derivative with respect to x of psi star d psi dx minus d psi star dx times psi. All of that integrated dx. Okay, so hopefully this is something that you remember from yesterday, or you have in your notes from yesterday. Okay, so this is exactly the same integral as yesterday, except that there's this extra factor of x, which wasn't in there yesterday. Okay. So when we were doing this yesterday and we didn't have this factor of x, then I said, oh, well, it's the, we take this thing, we differentiate it with respect to x, then we integrate it with respect to x, we're back with the thing that we started with. Okay, that was yesterday. Now, oh, there's this extra factor of x that ruins my story. Oh no, what will I do? Here's a trick. Let's integrate by parts. Okay, we can integrate by parts. That'll do it. Okay, so you guys remember about integrating by parts? You remember, I'll put it in green down here. If we say, well, integrate by parts. So that means that the integral of u dv is equal to uv minus the integral of v du. Does that seem sort of familiar from maybe your Calculus 1 class, right? Okay, well, that'll come in handy when we have something like this, okay? So let's take this whole thing and call it dv, because we know how to integrate it. Okay? And let's take just the x by itself and call that the u. Okay? So that means then that, let's see, I know u, I know dv, du is just dx, and v is the integral of this derivative. So it is just, whoops, wrong pen, that is psi star d psi dx minus d psi star dx times psi. Okay, so let's do the integration by parts. Okay, so my average velocity, that is going to be, let's see, uv. So it is x times all this stuff. Psi star d psi dx minus d psi star dx times psi, right? All of this evaluated from minus infinity to infinity, okay? And then minus the integral of v du, okay? So it's this, psi star d psi dx minus d psi star dx times psi, all integrated dx, okay? And then all of this is multiplied by the factor that I forgot about, which is this thing right here. Okay, so that's a constant factor multiplying everything. That is I h bar over 2m. Okay. Now, let's work with this thing. Okay. First of all, let's look at the term in the front right here. Okay. So we have x times all of this stuff at infinity minus x times all of this stuff and minus infinity. Okay. Well, we already talked about the same thing without the x yesterday. Okay. And yesterday, what I tried to convince you was the only way that psi can be normalized is if psi and psi star both go to 0 really rapidly as x goes to plus or minus infinity. All right. So these things have to go to 0. Of course, the x is going to infinity as x goes to infinity. But let's assume that these things go to 0 really rapidly, more rapidly than 1 over x. Okay, so that the product goes to 0. Okay, so if we say these things go to 0 as x goes to plus or minus infinity, more rapidly than 1 over x. Okay, maybe they go as 1 over x squared or as the exponential of x squared or something like that. Okay? And then if you take that thing even times the x, you still get 0 when x is plus or minus infinity. Okay, so then this whole term goes to 0. Okay, then what? Okay, well then we can say that the velocity average is equal to minus 1 over, no, minus IH bar over 2m. And then what? The integral minus infinity to infinity of psi star d psi dx. So that's the first integral, the first part of the thing up here. And then okay, plus IH bar over 2m, the integral from minus infinity to infinity of d psi star dx times psi integrated dx. Okay, so here's an answer. It's not too bad. It tells us how to extract the velocity out of psi and psi star. Okay, I could stop here, but I won't, because people conventionally simplify it a little bit more by doing another integration by parts on just the second term. Okay, so let's take this term and integrate by parts again. Okay, so for this term, I will say, let's let u be the psi, and dv could be d psi star dx times dx. Okay, And then what? du is d psi dx times dx. And v is psi star. Okay, and then what? We'll say the second term is equal to IH bar over 2m. Okay, now what? We have UV, so psi star psi evaluated from -infinity to infinity, and then minus the integral of v du. Okay, and so that is the integral of psi star d psi dx integrated dx. So in the second term, we look at this boundary piece first. Well, that's psi star times psi from -infinity to infinity. Well, but you already know the story here, right? Psi star and psi have to both go to 0 at plus and minus infinity. So blah, 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 you know the drill. This term has to be 0. Okay? So that term is 0. And so what we are left with is just another copy of the first term, right? That this second term here with the IH bar over 2m, it looks exactly like the first term. So I just get an extra factor of 2, which cancels the factor of 2 in the denominator. Okay. So our conclusion from this then is that the average velocity is equal to negative I h bar over m times an integral of psi star times d psi dx integrated over x. Okay, so this is a way that we could get out the velocity information, the average velocity information out of the wave function, okay, working with the wave function and the complex conjugate of the wave function. Now, people who do quantum mechanics normally don't talk about the velocity. Instead, people normally talk about the momentum instead. That is a standard thing in quantum mechanics, is to think about momentum rather than velocity. Okay, and so let's do that. Okay, so let's think about the momentum instead. Okay, so the average momentum should be, well, the mass times the average velocity. Right? Well, that's convenient because there was a mass in the denominator. Right? So we can just cancel that and we say the momentum is IH bar times this integral from -infinity to infinity of psi star d psi dx integrated over x. Okay, so that is a nice integral to get the momentum. Okay. There is a conventional way to rearrange these terms. Okay, let me show it to you. Okay. The way people normally rearrange these terms is to say, let's put the minus IH bar inside the integral in a funny place. Let's put it in the middle of the integral. So we'll say we have the integral from minus infinity to infinity of psi star times, let's put in here, minus I h bar, and let's put here the derivative operator, d by dx, acting on psi, integrated dx. Okay, so here you can see this thing is a derivative operator. And an operator always operates on something, okay? And the thing that it operates on is whatever is to the right, okay? It operates on the thing that it sees at its right, okay? And so, you know, when you have d by dx acting on some function f, x and y, whatever, okay? The operator operates on the f, okay? And it gives you df dx, okay? If you have a g of x and y times a d by dx of f and x of x and y, right? The way mathematical notation works is that the operator operates on the thing to the right, not on the thing to the left, okay? So this just means g of xy times df dx, okay? Operators operate on the thing on the right, okay? That's our mathematical notation, okay? So here we have our derivative operator that's operating on the thing to the right, which is just the psi. Right? So the operator operates on the psi and it produces d psi dx. Okay? So this thing means the same as this, right? So the minus IH bar has been put on the middle, and the derivative operator has also been put in the middle. Okay, so now when we do that, we get something which looks like another integral sandwich, right? It looks kind of like the integral sandwich for the position average, okay? Now it looks like we're making a sandwich, but now the meat in the sandwich is this operator. It's the combination of multiplying by negative IH bar and taking a derivative with respect to x. Okay? So we will say then that there is a momentum operator which is negative I h bar d by dx. Okay. And if we want the average momentum, we follow the same rule as for the average position. That is, we make this integral sandwich and we say we have a psi star times the momentum operator minus IH bar d by dx times psi of x and t integrated over x. So that is a way to calculate the average momentum, which looks very analogous to our way of calculating the average position. X and t times x psi x and t dx. Okay, so that's my theme of operator sandwiches. Now, let's see, how am I doing on time? Oh, actually, I have 15 minutes, don't I? I made a blunder yesterday. I think I ended class early yesterday. Ha! And you guys didn't even tell me. You guys probably all knew it, and you didn't tell me. Ah, you were just laughing at me the whole time, weren't you? Okay, I made a blunder yesterday, but now I've got you trapped. Ha! You can't get away for 15 minutes. All right, good. Well, then I can tell you about calculating averages of anything, right? If we want to calculate the average of anything, we put the average anything, we put, we change the classical x has to change to the x operator, and the classical momentum changes to the minus I h bar d by dx operator. And then you put it into this integral sandwich. Okay. So what kind of thing could you calculate, right? How about the kinetic energy? Okay, so classically, the kinetic energy is a half mass velocity squared, okay, which is the same thing as p squared over 2m. Okay, so now if we want to do the same thing in quantum mechanics, we would say that the average kinetic energy, that is the, wouldn't it be 1 over 2m times the average of p squared. So that'll be 1 over 2m times an integral of psi star, then we'll have a momentum operator, minus I h bar d by dx. And then another momentum operator, minus I h bar d by dx, operating on psi integrated dx. So this thing then, what does it produce, right? Well, you have one derivative here. So this acting on psi makes the first derivative. Then there's another derivative which acts on the first derivative. It makes a second derivative. Okay. And meanwhile, these factors of minus I h bar, they're just constant factors. Okay. So we get here, and I'll put the 2m inside the integral. So I could say integral of psi star, then we have constant factors. There's a 2m in the denominator. We have 2 factors of -1. That just makes a 1. We have 2 factors of I. That makes a negative. We have 2 factors of h bar. Negative h bar squared over 2m. And then a second derivative with respect to x of psi dx. Okay, so that's how you could calculate the kinetic energy. What else could we try to calculate following these rules? Okay, how about the acceleration? Okay, how about the acceleration, right? Well, for the acceleration, if we want the average acceleration, that would be the time derivative of the velocity. So that is 1 over the mass times the time derivative of the momentum. Okay, so that's the time derivative of, oh, we've got another one of these integrals. Okay, so the time derivative of psi star and then negative I h bar over m times d by dx of psi integrated dx. Okay, now we can go through the same kind of procedure as before. That is, we want to put the time derivative into the integral, and then we keep simplifying things, and we simplify by plugging in to Schrodinger's equation, right? So we, I'm going to skip some steps here because we've done this kind of thing twice before, and I don't want to do it a third time. Okay, so we put the time derivative into the integral and use Schrodinger's equation. And I'll skip a whole bunch of steps and get to the answer. Right? And this is all in the book, by the way, so you can read all the steps in the book. So this is 1 over the mass times an integral, and then we have the psi star. And what goes in here is something from Schrodinger's equation. Remember, Schrodinger's equation has the potential energy, V. So in here, when we use Schrodinger's equation and do integrations by parts and so forth, we get the derivative of this potential energy. V is the potential energy. So this whole thing then is 1 over mass times the expectation value of negative derivative of potential energy with respect to x. Okay, so here's a quiz. Have any of you ever seen a derivative of potential energy with respect to x before? In classical mechanics, can anybody tell me what is the derivative of the potential energy with respect to x?
Negative force.
Negative force. Yes, exactly. Okay. So this is minus 1 over mass times, well, negative force, okay? And so the minus signs cancel. And so we get that the acceleration average is 1 over the mass times the average of the force. Has anyone ever seen an equation that involves acceleration and mass and force before?
Newton's second law.
Newton's second law. Yes. So look, this is what it's saying, that the average acceleration is 1 over mass times the average force, okay? Or if I multiply through by mass, right, that the average force is the mass times the average acceleration, okay? And so this is like Newton's second law, but for averages, okay? And so it's saying quantum mechanics isn't exactly the same as classical mechanics, but when you go to calculate averages like this, then it is consistent with classical mechanics, okay? And this is a fancy thing that gets a name. This is called Ehrenfest's theorem, which says that the expectation values, the averages, obey classical laws. Like, for example, in this case, F equals MA for the averages. Okay. One more thing I want to show you in the last 3 minutes or so that I have here. Just going back to the Mathematica demos that I had earlier, I want to show you how I can actually calculate the momentum averages. Okay, so to calculate the momentum averages, okay, this is showing, let's see, am I showing which? I'm showing the wrong one. I wanted to show the other demo. Oops. Okay. If I want to show demo 1, here it is. Okay. So this is the one with the boring movie, right? Where nothing's moving anywhere. Okay. So in this case, I can calculate the expectation values. I already did the calculation for the expectation value of position. Okay. So here, I'll do the calculation for the expectation value of momentum. So the average momentum is now this sandwich, like I just derived for you, okay? So it is the integral of psi star times minus IH bar times the derivative with respect to x of psi integrated over all x. This comes out equal to 0, which makes sense because this is a system where nothing's moving in time, right? That the average position is staying fixed, right? But there's still an average of p squared, okay? That is the average of minus IH bar squared times the second derivative with respect to x of the wave function integrated over all x and that's not 0. Okay? So we get some average momentum squared. And then from that, we could calculate the variance, or we could calculate the standard deviation. That's what's the uncertainty in the momentum. Okay? So the uncertainty in the momentum comes to be h bar times the square root of this alpha parameter. Okay. Now you remember the uncertainty in x, it involves 1 over the square root of the alpha parameter, right? So if alpha is big, there's a small uncertainty in the position. There's a big uncertainty in the momentum. If alpha is small, there's a big uncertainty in the position, small uncertainty in the momentum. So there's a trade-off between those two things. Hold that thought, we'll come back to it next class, okay? But for now, I'll just quickly show you my other demo. And so if I go to share, demo 2, share, okay? And so here, this is the one where the probability is going back and forth like simple harmonic motion, okay? And we derived an average x that was like the cosine of omega t. And then I can derive the average momentum. So that's psi star times minus IH bar times the derivative with respect to x of psi, integrated for x is from minus infinity to infinity. And this comes out to be like negative sine of omega t. So it's like simple harmonic motion, right? If the average position is like the cosine, then the average momentum should be negative the sine. And we can get out the average momentum squared also. Okay, that is my story for today. So I will wrap it up. Please do really try downloading Mathematica and downloading these demos and see what you can do with those. And then I will see you guys on Thursday. But of course, I'll stick around and answer any questions for now.
Would you be able to share these notebooks with us?
Yeah, I'm going to put them on the Google Drive.
Okay, thank you.
Right, so I sent you that tiny URL thing in the syllabus. So if you go there, I will make a subdirectory for Mathematica demos, and I'll post both of those there. I'll do it a few minutes after class.